I'm Lоуренс Краусс, and welcome to a special edition of Science Matters from the Origins podcast from the Origins Project Foundation. I'm doing this because it's the end of the year and it's nice to have a celebration, but also to celebrate several other important things. First of all, this week, the Origins podcast passed 100,000 subscribers, and we're quite excited about that. And I thought in honor of that, I should do a special Science Matters. But also, this week, a very important event in science happened, and that was the launch of the James Webb Space Telescope. You've heard a lot about it, but I thought I'd spend some time, maybe more than you see in the standard television sound bites, talking about the science of the Space Telescope, what it might do, and why it's built the way it is. So this is a Science Matters holiday special, the James Webb Space Telescope. And I want to talk about the nature of the telescope. You may have seen these images a few times. The Hubble Space Telescope is basically a primary mirror, a mirror that looks for more or less visible light, as you'll see. It's got a little hole in the center, and its size was roughly about 2.4 meters across. And when you consider that the area of the mirror is pi r squared, and r is about 1.2 meters, you'd think it might be when you work it out, it might be greater than 4 or 5 meters squared. But when you have to take out the fact that that there's a hole in the center, and you work out to be it's about 4 meters squared. When you take the area of the big circle minus the area of the little circle, you get about 4 meters squared. And so that's the collecting area of the Hubble Space Telescope. JWST is built differently. It's much bigger, and because it has to be sent off in a rocket, just like the Hubble was, it has to be compacted, and it's made up of many segments, hexagonal segments, 18 hexagonal segments. Now, in order to reduce the weight of this, the framework of this is using a very light element, beryllium, which is sturdy but very light. And so the primary mirror of the James Webb Space Telescope is made of beryllium, and it's coated with a very thin layer of gold. And you've probably seen animations of how this honeycomb type structure grows out of a small structure that's all folded together in the telescope. And eventually it unfolds to be this shape. And the radius or the diameter of this shape is about 6.5 meters across. But of course, as you can see, it doesn't cover the entire sphere. And when you work out the collecting area, it's about 25 square meters. So when you compare the collecting area of the James Webb Space Telescope to the Hubble Space Telescope, you get a factor about 6.25 between 4 meters squared and 25 meters squared. And so it has basically a little over 6 times the collecting area. But there's something else that's important about it. It's looking, by the way, just one thing for those that may wonder about this gold layering. The layer of gold is about 10 to the minus 7th meters, a tenth of a millionth of a meter thick. But when you consider the amount of gold, a tenth of a millionth of a meter thick by 25 meters squared, you get about 48 grams of gold. That's the same amount of gold that you might have if you had a solid gold golf ball. So it's a non-trivial amount, and I suppose some space raiders in the far future might want to collect the gold from the James Webb Space Telescope. But it won't be easy to do because it's far out there. It's over 1 million miles away from the Earth. The telescope is large itself, but in fact, in order to protect it from not just sunlight, but particles and radiation coming from the sun, it's protected by a shield, a sun shield, that is often almost the size of a tennis court. As you can see, it's about 70 feet across by 50 feet across. And that shield protects the mirrors from the sun. As you'll see, it's always pointing away from the sun. But it also protects it from dangerous solar radiation. And the telescope is located at a position called the Lagrange point. First, after the mathematician Lagrange, who in an essay, a prize-winning essay, demonstrated when you have two bodies like the Earth and the Sun, there are a variety of special points that are stable in orbits that keep their position relative to the other moving bodies. There are 4 Lagrange points. Here's the Earth and the Moon around it. And of course, the Hubble Space Telescope is orbiting right around the Earth, about 100 or 200 miles above the Earth. But the James Webb Space Telescope is going out to another Lagrange point, which has been used by other telescopes in the past. The WMAP, Cosmic Microwave Background Satellite, is also in Lagrange point L2. It's about 1 million miles from the Earth. And because of the combined pull of the Earth and the Sun, an object at this Lagrange point will orbit the Sun at exactly the same period as the Earth. So as the Earth goes around, the James Webb Space Telescope will go around, and you can see if it's pointing outwards, it's always pointing outwards. I'll do that one more time. You can see that here it's pointing outwards. The solar shield is protecting it from the sun, and that will continue to be the case. So you can observe all of the time, unlike the Hubble Space Telescope, which is going around the Earth and therefore is periodically in sunlight and has to be capped during that time. The James Webb Space Telescope is always looking away from the sun. And this, by the way, this second Lagrange point is what's called an unstable Lagrange point. Namely, small perturbations will move objects away from it. So there has the James Webb Space Telescope, as the WMAP, Cosmic Microwave Background Telescope, has to have a little bit of jet propulsion and a few little thrusters to keep it stable during that time. And the James Webb Space Telescope has thrusters and such so that it can remain in a stable configuration at L2 for a working period of 5 to 10 years, which is its aimed working period. Much farther away from the Earth, therefore not accessible by space shuttles, even if we had them. It has to work properly the first time, and every time it can't be fixed as the Hubble Space Telescope was. But there's another very important difference between the James Webb Space Telescope and the Hubble Space Telescope, and it comes from what it's trying to see. Here's an image of looking back in the cosmos, and the point is, as we start out at the Big Bang and go forward in time, the cosmos gets bigger. It's expanding, and that's represented here by this wedge, which is expanding out. And as the universe expands, the wavelength of radiation expands with it, and so there's a relationship. You've often heard of the term redshift, but there's a relationship between basically the size of the universe today and the size of the universe at the time light was emitted from some object, and it turns out the wavelength of light we receive today compared to the wavelength of light that was emitted by that object, that ratio is 1 plus the redshift of an object. So a redshift of 0 is today, and that means that the wavelength of light we see is exactly equal to the wavelength of light that's emitted. So let me show you redshifts here. Today we have a redshift of 0. If we're looking way back at early galaxies, they're at a redshift of 1. That means the light is shifted so that the ratio of the wavelength today compared to the wavelength of light emitted is a factor of 2. But if we're if we try to go back to the earliest objects that the Hubble Space Telescope has seen, the quasars and such, they're a redshift of around 10. That means the wavelength of light is redshifted by a factor of 10 or so. The James Webb Space Telescope is designed to be able to look at the first stars, the first objects forming in the universe, as the universe went from the Big Bang to a hot, dense medium to the point where the cosmic microwave background first was emitted. That's the point where more or less matter became neutral and radiation could propagate throughout the universe. That happened at a very early time when the universe was about 300,000 years old. But between then and the time when the universe was maybe about a few 100 million years old, it's what's called the Dark Age. there were no stars. The James Webb Space Telescope is designed to look back to the period when the first objects, the first stars and galaxies formed at redshifts, we think, of 15 to 20. And that means we're looking at light that's redshifted by a factor of 16 to 21 or so compared to the frequency of light that was emitted when the objects first formed. Now, when you look at, this is an image, by the way, that comes, and I'll plug it from my new book, The Physics of Climate Change. This is the spectrum of light emitted by the sun in terms of the wavelength of light. This is the wavelength of light in microns. And you see visible light emitted from the sun here is more or less half a micron, peaks at somewhere in that range of half a micron, okay? Whereas, by the way, radiation coming from the Earth, which is at about 15 degrees Celsius, is in the range of many microns. But thinking now of redshift, well, let's just see. The Hubble Space Telescope actually is sensitive to radiation from about 1/10 of a micron to about 2.5 microns, spanning this full range in a sense. But you see, the James Webb Space Telescope, it turns out, is sensitive to some radiation, some visible radiation, but primarily radiation in the infrared band, in the micron. It goes from about 0.6 microns up to about 28 microns. So the James Webb Space Telescope is looking at near infrared and infrared radiation. Why is that? Well, if we think about redshift, if we're looking at an object like the sun, say a star like the sun, today at a redshift of 0, its radiation is peaking at half a micron. But at a redshift of 10, its radiation is peaking at 5 microns and a radiation of 20 at 10 microns. So you see, if you want to look at objects that are emitting light like the sun, or maybe even the first stars we think were hotter, so they'd probably be emitting radiation that's bluer over here. We want to be able to look, if we're looking at redshifts of 10 to 20, we want to be sensitive to this radiation band. And the Hubble Space Telescope isn't sensitive to that. Moreover, you can't build a telescope on Earth to look at this because the Earth absorbs radiation in this band as well. So that's why you need to if you want to look at this light coming from objects, the first objects that formed in the universe, at redshifts of 10 to 20 or 15 to 20, you can't do it in our atmosphere. And you can't do it with the Hubble Space Telescope. You have to build a special device like the James Webb Space Telescope, which is designed to look at the infrared to near infrared band. And that's why the James Webb Space Telescope was designed the way it was, to look at objects, the first objects that may have formed in the universe. And it's sensitive to the radiation, which is shifted compared to what it once was by a factor of 15 to 20. Now, there are a lot of questions we want to have when we're able to image the first stars and first galaxies that formed. We won't be able to image the first stars, but we'll be able to image the first galaxies that formed with the James Webb Space Telescope. We want to know a variety of things. What formed first? What were the kind of objects that formed first in the universe? Well, for reasons I'll describe in a second, we don't think they're galaxy-sized like our galaxies, but there's a big mystery too. We see quasars out to as far as we can now see with the Hubble Space Telescope. Quasars we think are massive black holes in the center of galaxies. But the question is one of the chicken and egg that I've talked about before. Which formed first, the large black holes, and did galaxies form around them? Or did galaxies form, or small galaxies form and cluster together and collapse to form the black holes? We'll want to see what formed first, and that will teach us about how galaxies formed, and also, as I'll describe in a moment, the formation of black holes. We also want to look and see how these early objects are clustered together. And I'll explain why that's kind of relevant in a second, because the science ultimately we want to see. We want to learn about how stars first formed. What were the types of stars that first formed? We think they were very large stars, very, very, very hot and large stars, because when there isn't many heavy elements in the universe, when lumps collapse, they don't fragment as much, and they should collapse basically more homogeneously into very large stars. And we think the first generation of stars were very large. And we'd like to see that. We'd like to see when galaxies formed and how they formed. We'd like to, as I say, see whether black holes form before galaxies or afterwards. And all of this is relevant to our understanding of the stuff that dominates the matter in the universe, dark matter, the stuff that we can't see. There's 5 to 10 times as much of it in our galaxy, probably 10 to 20 times as much of dark matter as normal matter, dominating all of the stuff in our universe. We think it's a new type of elementary particle, and I've talked about that. But the nature of dark matter will determine the formation, time, and sequence of all of those objects, stars, galaxies, and black holes. So if we can look out and look at that early generation of formation, the first stars and galaxies and black holes that formed, we'll learn not just about those formation of the kind of structures that are relevant to everything we see in the universe, including ourselves, but also the nature of the dark matter that dominates the universe. Here's the reason that we'll learn a little bit about dark matter. It's a little complicated, but I'll try and explain it. We think that the way gravity works, if we start out with lumps on all sorts of scales, the first objects to know that they're lumps will be the smallest objects, because gravity travels at the speed of light, and therefore larger lumps don't even know they're lumps early on. The first lumps to kind of form will be small, and we think that what will happen is that small sort of precursor galaxies or lumps of gas will form together, collapse, and then maybe merge with other clumps, forming ever bigger objects until we get to the galaxies we see today. But there's a feature here that we think is relevant to the nature of dark matter. Dark matter is necessary, we think, for galaxies to form, because there isn't enough time since the Big Bang, if normal matter is all there is, for small lumps of matter to have collapsed into galaxies, stars, and galaxies. That's because normal matter can't start to collapse until the cosmic microwave background formed, till matter became neutral, when the universe was about, as I say, about 300,000 years old, a redshift, I should have said, of 1,000. Before that time, when matter was ionized, when you had just protons and electrons hanging around, the electromagnetic forces were such that gravity couldn't compete, causing things to collapse. But once matter became neutral, then things could collapse. But normal matter, therefore, can't start to collapse until after this period of a redshift of 1,000, and there isn't enough time between then and a redshift of, say, 20 for galaxies to have formed, if that's the case. But if dark matter is there, dark matter doesn't respond to electromagnetism, and lumps of dark matter can begin to collapse earlier. And we think that due to quantum mechanics, lumps on all scales formed. And what you have are basically fluctuations, little lumps that form. You have them on many wavelengths. You have large scale lumps and smaller scale lumps. Now, the first objects that are going to collapse and become large, that cross a threshold large enough to quickly collapse to form galaxies, are going to be those lumps that have the largest densities at the time at a given time, because those objects that have the largest density at a given time will want to collapse. And if you think about small lumps on top of large lumps, what will happen is only rarely will you get lumps that are on top of these large scale wavelength lumps, the small lumps on top of them, and they will cross the threshold. And so what you'll get is a bunch of small lumps together that have crossed the threshold, forming, we think, galaxies or precursors to galaxies. And these will be clustered much more than other objects, because they'll be the small lumps that are built on top of these large lumps. So if we can look at the clustering, and that's what James Webb Space Telescope is going to do, it's going to look for clustered regions of precursor galaxies, we'll be able to see this kind of biasing, as it's called. The fact that the first objects to form are more clustered than the rest of the objects, because as the universe evolves, because gravity is attractive, the earliest lumps will collapse, but then later on, lumps that aren't quite as dense will collapse, and then objects that aren't quite as dense will collapse. And so you'll see that the objects that first form should be clustered more carefully than objects later on. And all of this depends on the nature of dark matter. So you'll see that as we look at the nature of these early objects that James Webb Space Telescope will begin to see, we'll try and understand not just their formation, but also the nature of the dark matter that's governing the collapse, the gravitational collapse of objects. Well, the other big thing that the James Webb Space Telescope is going to do, as you've heard, is going to be looking at exoplanets. And it's going to be looking at those exoplanets using a technique that's well described and well tested, and I've talked about before, this transit. The fact when a planet transits a star, it briefly blocks the light from the star, and so you can see the star dim a little bit. And that has been used by a variety of objects and telescopes that we've sent up to look at and discover many planets, literally thousands of planets around other stars in our galaxy. But the neat thing about the James Webb Space Telescope is not just that it actually has a coronagraph, so it's going to have a resolution of 1/10 of an arc minute, I believe, 1/10 of an arc second, I believe, which is enough to be able to potentially resolve and see planets not too far away in our galaxy. But it's also going to be able to, it has a very well precise spectrograph. It's going to be able to look at the spectrum of light. Now, when a planet goes in front of a star, its atmosphere will absorb light from the star that's behind the planet. And this has already been used to see one particular sodium-rich atmosphere of a planet. The sunlight goes through the planet, and if you look at the light, the starlight traveling through the atmosphere, you'll see certain absorption peaks or absorption troughs where the element, like in this case sodium, absorbs sunlight. Well, the spectrograph of the James Webb Space Telescope is going to be able to try and do that and look at light absorbed by planets, but also, by the way, light emitted by objects like planets, because remember, the Earth is at 15 degrees, is emitting in the micron wavelength. So if you're looking in the micron level, 1 to 10 microns, or in this case, 0.6 to 28 microns, you're going to be looking also at the radiation band that you might expect warm planets like the Earth to be emitting in. But here is another, this happens to be another image in my book, The Physics of Climate Change, where I talked about carbon dioxide absorption of sunlight and water in our atmosphere. But you can see that carbon dioxide and water absorb in the micron range. And if we look at atmospheres around other planets, we might look for not only just carbon dioxide and hydrogen, but organic materials. This is, if we look at a very small region here, and this is in frequency space rather than wavelength space, but the wavelength space it corresponds to is about 3 microns, we can try and look with the James Webb Space Telescope that it has the precision in its spectrum to resolve frequencies that are very narrowly separated, to look for absorption troughs from carbon dioxide, from water, from ethane, hydrogen chloride, methane, the kind of things like methane, and in fact, methane is a gas that in our atmosphere is often produced by life. Ethane, that none of these alone may be smoking guns of the existence of life. Oxygen also absorbs radiation, and there was no free oxygen in our atmosphere before life, but there is now. Of course, oxygen doesn't really absorb in the infrared band, but we can look for organic materials in the atmospheres, and if we see, depending upon the ratio of these, if we see ratios that are comparable to the kind of ratios that life have produced in the atmosphere of Earth, if we look at enough absorption troughs, we might be able to get evidence of something that we think is evidence of an atmosphere like Earth's atmosphere today, which has really been determined, as you know, by the nature of life. Life is determined both not just the fact that oxygen is in the atmosphere, but other things like methane, and of course, intelligent life is also affecting the carbon dioxide in the atmosphere. So the ability of the James Webb Space Telescope to image planets, but also to look at planets transiting stars and planets where we know they existed by using Earthbound and other space telescopes that have told us where those planets are. The James Webb Space Telescope can focus on those planets, try and look at the atmospheres of those planets when they transit their stars, use the spectrograph to look for the composition of the atmospheres, and between directly imaging and spectroscopically imaging the atmosphere, we might be able to look not just at how planets formed, but more importantly, perhaps the question that everyone asks is, are we alone in the universe? And well, we might not consider microbes to be very good companions in the universe, but if microbes can exist and early forms of life can exist elsewhere, then it bodes well for the possibility that other forms of life, including perhaps intelligent life, might exist in the universe. Those are some of the science goals of the James Webb Space Telescope, and the reason it has the properties it has, its size, its ability to resolve small objects and small galaxies in the early universe, its spectral sensitivity in the micron range, the infrared range, why it looks at infrared radiation to look at early stars, early galaxies, and learn about the first structures in the universe and the nature of dark matter, and then also to be able to look at radiation that's absorbed by planets around stars elsewhere in our galaxy, as well as looking at radiations emitted even by giant planets and moons and other things even in our solar system. So the James Webb Space Telescope is multi-purpose. It's going to open up new windows on the universe to look at the first structures that ever formed and the atmospheres of planets. And as I've said many times before, every time we open a new window on the universe, we're surprised. And I'm sure we're going to be surprised. And in 6 months or so, when the James Webb Space Telescope starts taking data, our picture of the universe will change dramatically. And maybe a year from now, in A Science Matters, I'll be able to talk about some new discoveries about the nature of the universe, dark matter, and life. What an exciting time to be around. Enjoy your holiday and enjoy pondering the universe around us. You take care.
I hope you enjoyed today's conversation. You can continue the discussion with us on social media and gain access to exclusive bonus content by supporting us through Patreon. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit originsprojectfoundation.org.